Hi, and welcome to the final part of the solution for problem 4.3, where we will determine whether the inverse gamma distribution or the Pareto distribution has the heaviest tail. So one thing that you might notice when you're trying to look for the Pareto distribution in the book is that its density is not given in chapter 4. I think it's actually introduced in chapter 2. So remember, for Pareto, look at chapter 2. I think you can also find the distribution function, the mean excess function, survival function, and everything else on the Pareto distribution in chapter 2. So look there. Now another thing that's kind of interesting is that in chapter 2, the Pareto distribution is introduced as the distribution with parameters alpha and theta. And then you might say, oh no, our distribution is given with the parameter gamma instead of alpha. But just remember that gamma is just a placeholder for any kind of value. So you just plug in gamma there, the place where you see alpha in your formula, and you're safe. And some of you might ask why we use gamma here instead of alpha, if there's a special reason for that. And yes, there is, because if we write alpha here, then it could easily get mixed up with the alpha that we use up here. We would have to use two different colors to just remind ourselves of the fact that these two alphas do not stand for the same thing, which is why we choose to use gamma here in the expression for the Pareto density when we compare the two density functions. So just before we get started, the assumption that we have on alpha and beta and gamma and theta, so the assumptions here are all that they are strictly positive. And now I think we are ready to get started. So once again, we consider the ratio of the densities. Consider the ratio of the densities, which is given as h of x equal to, and I think I will just choose to put the inverse gamma density on the top. So the inverse gamma density in the numerator, parameters alpha and beta, divided by the Pareto density in the denominator with parameters gamma and theta. And this is proportional to, so when I say proportional to, I mean that it is equal to this thing here multiplied by some constant. So I can remove the constants in the expression. So this is proportional to x to the minus 1 plus alpha multiplied by e to the minus beta over x divided by theta plus x to the minus 1 plus gamma. So we can kind of do the same trick as before, where I take the log on both the denominator and the numerator. But the thing is that well, nothing really special happens with this when x goes towards infinity, right? Because when x goes towards infinity, the exponent goes towards 0, so this exponential expression goes towards 1 as x tends towards infinity, which means that essentially the only thing I'm interested in is this and this. And just for good measure, since this is in a minus power and this is in a minus power as well, I can just flip them over and have positive exponents instead. So I put this in the numerator and this in the denominator. And then I have the e to the minus beta over x, which is essentially non-interesting. So the only interesting thing here is what happens to this ratio when x goes towards infinity, since this expression just goes to 1. So essentially what I have is an expression where I have x to the power 1 plus gamma divided by x to the power 1 plus alpha, right? This is essentially what I have. And how does that look for x going towards infinity? Well, we know that the higher the power, the more the term dominates. So it's essentially a question of, is gamma largest or is alpha largest? So again, we have to split this up into cases. So if gamma is greater than alpha, then we have x to a greater power here than down below. Then h of x will tend to infinity as x tends to infinity, because then the numerator will swallow up the denominator. And then, so thereby, the inverse gamma distribution has the heaviest tail. However, if alpha is greater than gamma, then the denominator has x to the highest power, so that will grow quickest towards infinity. So then h of x will tend to 0, right? As x tends towards infinity. And then that means that the Pareto distribution has the heaviest tail. Now, we are not completely finished yet because there is still the last case, if alpha is equal to gamma. So what happens if alpha is equal to gamma? First and foremost, we note that even if alpha is equal to gamma, then these two expressions will never be equal. So the densities will be different. So the two distributions are not equal, even though gamma is equal to alpha. But if gamma is equal to alpha, then this term, then h of x will be equal to gamma over x, theta over x plus 1 to the 1 plus gamma, right? Because then I can just take the denominator and put it up into the parentheses, and then multiplied by e to the minus beta x. And this thing will just tend to 1 as x tends to infinity. And what does that mean? Well, that means we don't have the case where the inverse gamma tail swallows up the Pareto tail, and we don't have the case where the Pareto tail swallows up the inverse gamma tail. Hence, the two distributions have equivalent tails. So that just means none is more heavy-tailed than the other. So again, in this exercise, part D, we have 3 cases, just as we had like 15 cases in part B, and that is also why each time you write down the densities for whichever distributions you're looking at, it's also important to remember which values the parameters take on, and to take into consideration that for different values of these parameters compared to each other, the results might vary.